Okay, so this is projectile motion of an electron in a parallel plate. So we're trying to find the velocity after this electron leaves the plate. So basically what happens here is an electron is going to get shot into the parallel plates at 5 times 10 to the 6 meters a second. And then it's going to go kind of like a path like this. And then it's going to come out the other side. It's going to have a final velocity. So it's going to be accelerated in the plates here, right? Because this is the negative side over here. So it's going to get pushed up like this from an electrical force. And therefore it's going to accelerate up this way. And then it's going to have a final velocity over here. So we also have the length of the plates, and then the height of it, and then also the voltage of it. So using this information, we can find the final velocity. So it's kind of like a projectile motion problem here, because it's going to have constant acceleration inside the parallel plates. So we can therefore find the final velocity using projectile motion equations. So first things we're going to do, let's find the flight time. So the electron is going to be in the plate for as long as it takes to go from this side to that side, right? So we know the length of the plate, and then we know the speed, so we can find the time this way, right? So equation we're going to use is delta dx equals delta t and then vx. So we're just going to rearrange for delta t. So delta t is going to equal delta dx over vx. Okay, and then I'm going to skip forward to fill in our numbers here. Okay, so I have our time here. So flight time is going to be 5 times 10 to the negative 8 seconds. So it's going to take that much time to go from that point right there to this point over here. Okay. So now using this, we're not going to use it right away, but the next thing we need to do is find the acceleration, right? So let's use Newton's second law. So acceleration equals F net divided by mass. And now the only force acting on this is the electrical force, right? So we're going to do acceleration equals force electric divided by mass. And now the electrical force in this case is equal to, well, it's Q multiplied by the electrical field, right? So the electrical field like this, but we don't have the electrical field. We have voltage and we have the distance. We can find electrical field because electrical field is also equal to delta V over delta D. So they're equal to the same thing. So 120 volts divided by 0.2 meters will get you the same answer. So let's plug that into our equation here. So acceleration is going to equal Q delta V over delta D divided by mass. So I'm going to skip ahead and plug in all the numbers and then put the answer into my calculator. Okay, so also just one thing. So I filled in, this is supposed to be acceleration in y, so I just replaced that because I didn't actually talk about that before. And then I filled in for all my numbers. So that is the elementary charge right there because we're dealing with an electron. And then of course, we already talked about those two. And then that's the mass of the electron. So that'll get you acceleration in y. And now we're going to then use this number from up here, multiply it with acceleration, and we should get the final velocity in y. So let's do that. So VF equals acceleration. Oh, this is in y. Acceleration in y multiplied by delta t. So I'll skip ahead and write in that now. Okay, so we got the number there, and now we know what the x and the y component is of our final velocity. So now we just need to put the two things together. So we're going to do Pythagoras theorem to get the magnitude, and then we'll just use trig, the tan inverse, to find the angle. So let's do Pythagoras theorem first. So I'll skip ahead to that. Okay, and then that's the magnitude. So I'll just draw magnitude in there. So that's the magnitude of this. But now we need to find the angle. So I have a little bit more space left. We're going to do, actually before I do that, I'm just going to draw out what this will look like. So here, there's not too much space. I'll draw Pyrthos. So let's see. So we still have the x component. The x component is going to stay the exact same, right? So I'll just write x there. So it's completely parallel to the parallel plates. So it's going to be completely in the x-axis. So it's like this. And then the y component is slightly larger than that. So it's like a little bit larger. I'll just exaggerate a little bit. So there we go. And that's the y component. So that's y, that's x. And there's going to be a theta. Now the theta is going to be very close. The theta is going to be very close to 45 degrees, right? Because, like, let's look at this, right? So it's 5.27. This one is just 5. And then they're both times 10 to the 6. So they're going to be very close to 45 degrees. And that's theta in there. So I'm going to do opposite over adjacent. So tan, actually, I'll do theta equals tan inverse and then opposite over adjacent, so 5.27 I'm going to leave out the times 10 to the power of 6 because you don't really need to do it. And then that should get you the answer of 46.5 degrees. There we go. And then we can put that all together. So VF should equal 7.27 times 10 to the 6 meters a second, and then 46.5. Oh, sorry. So write 46 point, no capital R. So write 46.5 degrees up. And that should be your final answer. So let me know in the comments if you have any questions at all.